Introduction to Sedimentary Rocks and Sedimentary Rock Identification. Clastic sedimentary rocks or detrital sedimentary rocks are principally made up of fragments derived from pre-existing rocks or minerals and transported some distance from their place of origin. About 75% of all rocks we see exposed at the Earth's surface are sedimentary. As geologists, we study these rocks to reconstruct the Earth's history. They are also important to us in an economical sense, as that they're important sources of coal, oil, gas, iron, aluminum, sand, and such. If we look at the formation of sedimentary rocks, we can break it down into 4 steps. The first being weathering, second, transportation, third, deposition. This occurs when a geologic agent can no longer transport the material and deposit it at a new location. And finally, lithification. This is the formation of the rock itself. In step 1, weathering, we see a breakdown of pre-existing rock. This could be through mechanical means like ice freezing and wedging pieces, or chemical means like acid rain. This then turns the rock into sediment or fragments. In step 2, that sediment is transported. Transportation can take place due to wind, water, or even ice. You can tell if a sediment was transported a long distance or a short distance by examining 2 features, one being the sorting and the second being the rounding of the sediment itself. Sediment that's traveled a long distance will be rounder in nature, as we see over here to the right. Sediment that's close to its source, that hasn't traveled very far or has traveled a short distance, will be very angular in nature. When looking at a sediment's sorting, if sediment has only moved a short distance, we'll see a poorly sorted sediment, like over here on the left, meaning that we have various grain sizes, from small to large. If it's been transported a long distance, then we'll see grain sizes that are pretty much the same or almost equal in size, as we see over here on the right side of the page. The third step is deposition. After transporting the sediment, which requires some energy, there is a relationship between grain size and energy. Smaller grains take less energy, bigger grains take more. If a river slows down, sediment will actually drop out. This will be the larger pieces first. As the river begins to speed up, the water can pick up larger pieces of sediment and transport larger bits of. In step 4, which is lithification, we may have compaction, which is pressure that might be applied due to overlying sediments that pack in on top of the original sediment. This results in grains being squeezed as well as water from the pores themselves. Finally, we have cementation. This is where the pore spaces are filled with ions that precipitate from the water. The most common are going to be some type of a calcium carbonate like calcite, or a silica like quartz. Thirdly, iron oxides. The source of the sedimentary material may be detritus, which is broken up pieces of rock, like gravel, sand, silt, clay, derived from the erosion of land surfaces, or chemical precipitations, precipitation of dissolved materials from water, direct precipitation. Plants or animals extracted chemicals from the water to form shells, skeletons, etc. Also, when animals die, shells are also deposited. If we look at the detrital sedimentary rocks, or clastic sedimentary rocks, these are composed mostly of things like quartz and feldspars and clays. We classify these based on their particle sizes, the grains that make up the rock itself. Not the size of the rock, but the grains within the rock. If we have grains within the rock and the majority are greater than 2 millimeters in size and rounded, we have a gravel. If they're rounded, it's a conglomerate. If we have a gravel with greater than 2 millimeter angular grain sizes, then it's called a breccia. When we have a rock with 2 millimeters to 1/16 of a millimeter predominantly, this would be a sand size grain. These would be referred to as sandstone. Sandstones, when they're 2 millimeters, can easily be identified. The grains can be seen. When they're down to 1/16 of a millimeter, however, it's impossible to identify visually. In this case, though, we can still identify it by touch. In touching a sandstone, it will feel gritty, just like a sandpaper. Siltstone is 1/16 of a millimeter to 1/256 of a millimeter in size, and clay is anything less than 1/256 of a millimeter in size. With silts and clays, it can be difficult, even with touch, to determine which you have. If you get to the point where you've identified whether or not you have a silt or a clay, to determine which one, the easiest method is to actually put it in your mouth and chew on it. Silts, you'll be able to feel this between your teeth. It'll taste gritty. Clays, on the other hand, will taste mushy or smooth between your teeth. So let's look at some common detrital sedimentary rocks. If we look down here on the left side, we can see a rock. We can easily see the different pebbles. A quarter's in here for scale. We can also, by looking at these, see that most of the pebbles inside are kind of rounded off. This would be an example of a conglomerate. The one down here at the bottom is a little bit easier to see the pebbles. The individual pebbles are rounded and stuck inside its matrix. So this is also a conglomerate. Up above here we can see another example, but these are angular chunks or pieces, very angular, and this would be an example of a breccia. Sandstones, when we look at them, oftentimes have grains that are too small to see with the naked eye, but we could still feel the grittiness to the sandstone between our fingers if we were to pick it up and touch it and hold it. We can see up here some 3 examples of sandstones. Sandstones come in a variety of colors. Sometimes they may even show the bedding planes within the rock itself. Other ones, on the other hand, may be just solid one color, sand. Down here below we have an arkose. This is a kind of a sandstone, but it's got a lot of potassium feldspar, which are the pink grains within inside it. Going on to a siltstone. Siltstones can look a lot like sandstones, but again, the grain size is what tells the difference. With a siltstone, it may look kind of like a sandstone, but you may not be able to feel the grittiness to it. Again, you could chew on it to tell if it's gritty or not, though. And this is a shale. Shales, some shales will be solid colors, others will have banding of colors. We see the layerings in here with the individual bedding. These are made up of clay. Going on to chemical sedimentary rocks. When identifying chemical sedimentary rocks, they're identified by composition. So in identifying these, you will need to read up from your lab manual on the different types of chemical sedimentary rocks and read their descriptions as well as their chemical compositions for identification. We can actually break chemical sedimentary rocks into 2 types: a physical, which might be anything that occurs due to evaporation or evaporites. These are things like salts and gypsums that evaporated out of the rock. Once they evaporate out and are deposited as a rock, then we refer to them as a rock salt or rock gypsum. The biochemicals come from water-dwelling plants and animals that extract the calcite, which is the calcium carbonate, and quartz from the water to form their shells. On death, the skeletons accumulate on the seafloor as a detritus. Another type of biochemical would be something like a coal. This is preserved organic material formed in a swamp. Here we have some examples of some evaporites. Up at the top we see that we have a salt. This one's a pink salt, but salts can be pink, rock salts can be pinks, whites, blues, grays, browns. The best way to identify them is through taste. Down below that we have some rock gypsum. Both of these images are of rock gypsum at the bottom. One is showing some varns, so some layering in here from black to white, and the other one looks kind of pinkish to white in color. The main way to identify rock gypsum is it's very soft. You can powder it by digging at it with your fingernails. The chemical and biochemicals, here are a few more. Another example might be a coquina, which is a sedimentary rock made up of fragments of seashells that have been glued back together. Another one might be a limestone. Down here below we have a limestone, and this particular limestone is actually a fossiliferous limestone in that it also contains fossils within the limestone itself. We have a bituminous coal up above, so this is from essentially the breakdown of, or compaction of altered plant remains. And then finally we have down here at the bottom an oolitic limestone. These little circles that you see inside here are called ooids, and they've been cemented together to create this limestone. In summary, detrital sedimentary rocks are going to be identified based on their grain size. So you're going to be looking at gravel, sand, silts, and clays to identify the detrital sedimentary rocks. With the chemical sedimentary rocks, these are identified based mainly on mineral composition. This is their key. So in identifying these, you will need to read up on their descriptions from your lab manual to correctly identify the chemical sedimentary rocks. All right. Variations, more than one particle size is another thing that you can use, the sorting. Remember, with the conglomerates, you're going to have varying sizes, if you remember back from the image, of grains. Some chemical rocks can also contain detritus, like we saw in the coquina, which is broken up fragments of seashells, and detrital rocks are cemented by material originally dissolved in water. So this concludes an introduction to sedimentary rocks and sedimentary rock identification. Remember, with the chemicals, to read the descriptions for their identification.